Hello, this is Mr. Bradley, and today I want to talk to you about Newton's first law. Newton's three laws are the laws that we use in physics to talk about forces and what forces make things do in nature. Newton's first law actually addresses the situation when there is either no net force acting on an object or just no force acting on an object at all. Newton's first law says that an object will stay at rest or in motion with a constant velocity unless acted on by an unbalanced force. For this reason, sometimes I like to call Newton's first law the constant velocity law. It basically talks about why things that are just sitting there will keep sitting there. And it also tells you why things will move with constant velocity if they have no resisting force acting on them. In this diagram on the page, we have a screenshot from a demonstration that we did in class. What we have is an embroidery hoop with some quarters sitting on top of it. And while those quarters are just sitting there, we show that there are actually two forces acting on the quarters. There's the force of gravity, which we also call the weight. We label that Fg. And there's also a balancing force of that called the normal force, which is really just the force of the needlepoint hoop pushing back up on the quarters. In this scenario right now, these two forces are balanced, and so like we say right here, there's no change in motion. Another way to say that is that there's no acceleration. The quarters are just sitting there with a constant velocity. It just turns out that that constant velocity is zero. Now, in this next screenshot, what I've done is I've pulled the embroidery hoop out from underneath the quarters in such a way to where the hoop did not disturb the quarters at all. So now what you actually see is this great screenshot where the quarters are just basically floating in space for a moment as I took away the normal force. Now, at this point, the forces are unbalanced and the quarters are going to start to accelerate, but they just haven't done that yet. Newton's first law is sometimes called the law of inertia, and I will talk about why that is on the next page. Okay, so inertia is one of those words that gets used in everyday language a lot. The definition of inertia is that it's an object's resistance to changes in motion. That means its resistance to acceleration. If something has inertia, it's difficult to get it started moving, and it's also difficult to stop it moving. But also, a very interesting side part of that is if something has inertia, it will just keep on moving even though there's no force acting on it. If you put something in a frictionless environment, it continues to move with a constant speed in a straight line because of its inertia. So we have some examples right here where you could think about some everyday items that have not very much inertia and something that have a lot of inertia. You know, something like a fly, it's easy to accelerate it. It's easy to make it speed up, slow down, change directions. But something like a Greyhound bus, that's much more difficult to do. Once it gets going, it's very difficult to stop. Inertia really relates to a concept also known as momentum. That is really just like a logical consequence of Newton's first law. That'll be something we study in a later unit. The most important thing I want you to get right now is that the quantity that we call mass is really just a quantitative measurement of an object's inertia. If you say that the mass of an object is 1 kilogram, what you're really doing is quantifying how difficult it is to make it accelerate. If you held a 1 kilogram mass in your hand and you tried to shake it back and forth, the resistance that you feel as you're doing that, you're really feeling the object's inertia. If you picked up something that was more massive than that, you know, a 2 kilogram mass or say even a 10 kilogram mass, and you tried to repeat it, you find that it's much more difficult to accelerate that. Oftentimes people associate that with weight, but the fact of the matter is inertia is completely independent of the force of gravity. If you took those masses out into space and did the same demonstration that I was talking about, you'd find out that they are very, very difficult to move or accelerate, just like they are on Earth. However, once you get them moving, they will also just keep moving under their own inertia, if you will. Because they have momentum and because they're in motion, they will just continue to move in a straight line at a constant speed. One last page of notes that I want to discuss is this page where we talk about forces acting on an object. Many of the situations that we look at, we spend some time trying to look at all the different forces that are acting on an object. And this table really summarizes the different ways forces can be combined. For instance, there might just be a single force acting by itself, or you might have two forces acting on an object in the same direction. You could have two forces acting in opposite directions, and a very special case of that is two forces acting in opposite directions that have the same magnitude. Of course, you could also have two forces acting on an object in completely different directions, in which case you would have to do a vector problem here. The thing to notice is that out of all these situations, there's only one scenario where the forces are balanced out. This one scenario is the only time that you would consider Newton's first law. In this situation, if you had equal forces that were in opposite directions, the object would either be at rest or it would be moving with a constant speed in the direction that it had already been moving in when these forces came in. I'm going to show you a simulation on the next page to help you think about some of those scenarios. Okay, so this is a simulation from the PhET website called Forces in One Dimension. And in this simulation, there's a lot of things you can do. We'll look at some of the controls over here. You can see a window that shows the normal force and the force of gravity acting on the object. In this case, the object in question is going to be this filing cabinet. This filing cabinet has a mass of 200 kilograms. That means it has quite a bit of inertia. If I want to overcome that object's inertia, I'm going to have to put a force on it to make it start moving. Also in this simulation, you have the ability to turn friction on and off. Well, I actually want to turn friction on for this simulation because that really helps me see some of the Newton's first law scenarios that I want to look at. As I look down here, you can see that I could show graphs of applied force, I could show graphs of acceleration, I could show graphs of velocity, or I could show graphs of position. Well, honestly, I'm not going to show any of those graphs in this simulation because that actually clutters up what I want you to see. I simply just want you to see what happens when forces are applied to this filing cabinet and sort of judge the motion of the filing cabinet after that. The last thing to notice here is this box that says applied force. That will have the values of the force that I'm using, and that'll be important for me to be able to figure some things out. So first things first, what I'm going to do is use this stick figure guy to just put a force on the filing cabinet. Now I'm just using the mouse and I'm pushing it over and I'm having him push harder and harder. I mean, look at how he's like leaning down as he pushes farther. Pretty funny, really. Well, what I want you to notice is that in that applied force box, it says 306 newtons. That's how much force that my stick figure guy is using. Now, right now, the filing cabinet is not starting to move, and that's because there's a force of friction acting on that filing cabinet that's at least equal to the applied force that I'm putting on it. And that will happen up to a certain point. And after I get to a certain point, I can apply too much force, in which case then I can make it start to move. Well, if I let that force go, you can see the friction acts and it starts to stop. That's examples of Newton's second law. What I really just want to talk about here is Newton's first law. Newton's first law says that as long as there is not an unbalanced force greater than zero, then objects will not accelerate. And you can pretty much see that that's the case right here. If you look at the box in the top right-hand corner of the screen, you can see that the applied force equals the force of friction in every situation, just like the normal force equals the force of gravity, and therefore the thing continues to stay at rest. Now, here's where it gets kind of interesting. If I apply enough force to make this thing start moving, and then I quickly pause my simulation, I can't do it quick enough. So what I'm going to do is I'm going to start the file cabinet moving, and then I'm going to remove the force that I used to make it happen. And I will show that happening for you in the simulation. Okay, so what I've done is I've applied enough force to the filing cabinet so that the filing cabinet will start to move. And then what I'm going to do is I'm going to put enough force that equals the maximum force of friction, which I believe might be around 400 newtons. Now, when I hit go, you can see that the applied force is basically equal to the friction force. And when that's happening, I want you to notice that the file cabinet moves with a constant velocity. What keeps the filing cabinet moving is the force that's applied, but that's only because it has to overcome the friction force. The force applied is equal to the force of friction force. The net force between those two forces is zero, and the object moves with a constant velocity. That's Newton's first law. Now what I've done is set up a scenario to where I'm applying enough force to make the filing cabinet start moving, but I want you to notice that I've turned off the friction. So right now the only applied force is in the forward direction, and there is no friction force going backwards. What I'm going to do is I'm going to remove that frictional force, or that applied force, and I'm going to hit go, and I want you to notice what happens. The filing cabinet just continues to move because I'd already started it moving with the applied force, and now by taking away the applied force and there's no friction acting on it, it just keeps going at a constant velocity. That's a perfect example of Newton's first law. You could think of lots and lots of scenarios where this would be true, but the simplest scenarios would be if you took a hockey puck and slid it across very smooth ice, or if you used an air hockey puck on an air hockey table. All of those show the example of an object continuing to move at a constant velocity because there's no friction acting on it. If you put it in motion, it'll stay in motion unless acted on by an outside force. So that is a good summary of what Newton's first law is, and all of that will lead logically into what Newton's second law is. So if you need to watch that video, then go find that one.